So this is week 8, and I'm going to be covering how to solve logarithmic equations. So first off, what is a logarithmic equation? So this is simply an equation that has a logarithm, and the variable is inside the logarithm. So you could have logarithms with like numbers, where you're taking the log of a number, but specifically if your variable is inside the logarithm, that's what makes it a logarithmic equation. So we have two ways of solving. One is using the one-to-one property, which is used if you have two logs that are equal to each other and they have the same base. If that is true, then their insides are equal. And if you can't solve using the one-to-one property, then we solve using the inverse property, where essentially if you have an exponent or exponential with a log in the exponent, that cancels out and you're left with what's left over, the variable essentially. Now, unlike when we're solving exponential equations, when we solve logarithmic equations, we always need to check the domain, because anything that you're taking the log of, whatever's inside the log, has to be greater than 0. So you have to make sure that whatever answers you get don't make the log negative or 0. And then you also need to just generally check your answers, because sometimes you end up with extraneous solutions, or you get extra solutions that are not actual solutions to the problem. So there's a couple checks that you need to do. And if you check your answer, then you're inherently always checking the domain as well. So the basic rule is just make sure you check your answers afterwards so that you know whether your answer actually works or not. So the one-to-one property, that says that if you've got b, x, and y, and these are all real numbers, so b is the base of the log, that has to be greater than 0 and not equal to 1. So you've got these two logs that equal to each other with the same base, then the insides are equal. And so our textbook calls this the equivalence property of logarithmic expressions, but other textbooks call it the one-to-one property. So I'm going to start by solving logarithmic equations using this property so you can get a handle on that, and then we'll move on to using the other property. So here we're solving the log of 3x plus 4 equals the log of x minus 10. So if there's no number under the log, no subscript, that's assumed base 10. So this is going to be base 10 log. And just to kind of talk about the domain, whatever is inside here needs to be greater than 0. So 3x plus 4, whatever you get for x, when you plug it in there, that needs to come out to be greater than 0. So we can solve this to find out that 3x has to be greater than negative 4 if you subtract 4 from both sides. And then if you divide both sides by 3, you find out that x has to be greater than negative 4/3. So we just have to keep that in mind, that when we're solving, whatever value we get for x has to be larger than that. And the other log also gives us some restrictions here, because the inside of that one also needs to be greater than 0. So x has to be, x minus 10 needs to be greater than 0, which tells us that x has to be equal to 10. So if we were to look at these two inequalities on a number line, because both of these things need to be true, which is an AND statement, we've got negative 4/3 and 10. So one of them is saying that we need to be greater than negative 4/3. So I'm just going to kind of put it above. The other one says we need to be greater than 10. Our solution needs to be the overlap of these two things. So whatever we get when we solve needs to be greater than 10, because that's where these two inequalities are overlapping. So we need to just make sure when we solve that whatever we get for x, it's bigger than 10. So once you've kind of determined your domain and what values you're allowed to have for x, then we can actually go and solve. So I'm going to rewrite what we've got here. We've got the log of 3x plus 4 equals the log of x minus 10. So the one-to-one property basically says if you've got the same base, we have a log equals a log, the insides are equal to each other. So we have 3x plus 4 equal 2x minus 10. So now all we need to do is solve for x. We've got a linear equation here, so we're just going to solve for x. So I'm going to start by, I'm going to put my x on the left, so I'm going to subtract x from both sides. So that gives me 2x plus 4 equals negative 10. Then I'm going to subtract 4 from both sides. And we get 2x equals negative 14. And then when we divide both sides by 2, we get x is equal to negative 7. So our answer is kind of over here on our number line. So we are outside of our possible answers. So we got an answer, but it doesn't work. And we will check our answer just to be safe. So if I'm going to check to double check that this negative 7 is indeed not going to work because it's not where we're expecting our answer to be, we will plug it in. So we'll have the log of 3 times negative 7 plus 4 equals the log of negative 7 minus 10. So when I simplify 3 times negative 7, that's negative 21 plus 4. And then on the right side, negative 7 minus 10 is negative 17. And then we've got the log of negative 17 equals the log of negative 17. So you might look at that and be like, aha, but the left side equals the right side. Well, yes, but if you did the log of negative 17 in your calculator, you're going to get an error because we can't take the log of negative 17. We can't do it. So even though the left side equals the right side, it doesn't actually work in our domain. So this is what we call an extraneous solution. It's a solution but doesn't actually work when you try to evaluate it. It's not part of our domain, which is why we want to look at the domain and kind of draw that picture. So this problem actually has no solution because the solution we did get doesn't actually work. And we can look at this graphically because sometimes graphing makes things, easier to understand. So I'm going to bring up Desmos and go to the graphing calculator. So graphing, what this means is basically if we took this left equation and graphed that, and then we took the right equation and graphed it, we're looking for the intersection. We're looking for where these two things are equal. So I would be typing into Desmos each of these graphs, or basically each side, and then looking for where they overlap. So I zoom out, you can see, okay, they're never actually going to overlap because you can see as I go to the right, they basically are staying the same distance apart here. They are not going to overlap. So that's why there is no solution. And so you can graphically check your solution by basically seeing, does the left side equal the right side? Do they intersect? Are there any questions? Okay, so here's another one. This time, this is base 5. It really doesn't matter when you're solving as long as it has the same base on the left and the right. And we're going to do what we did before. We're going to look at the domain so we know where to expect our answer, where our answer should be. So 15 minus 4x needs to be greater than 0. And if you subtract 15 from both sides, you get 4x needs to be greater than negative 15. And then when I divide both sides by negative 4, remember that that changes the direction. And this will become x is less than 15 over 4. On the right, we just know that x has to be greater than 0. So I'm going to draw my number line. Let's see. The logarithmic stuff brings in all the things we learned basically in the first week with the linear inequalities. So I've got 0 and 15/4. And we know that x has to be less than 15/4, so that's going to be going to the left. And x has to be greater than 0, so that's going to the right. So our answer is where the overlap is. So our answer must be between 0 and 15/4. So we just have to keep that in mind when we solve, that that's where we expect to find our answer. So I'm going to write down our problem. We've got log of 15 minus 4x equals the log base 5 of x. And it has the same base, so the insides are equal to each other. So this tells us that 15 minus 4x is equal to x. So in this case, for solving, I'm going to move my 4x to the right since I've already got the x by itself on the right. So I'm going to add 4x. And this gives me 15 equals 5x. And then we'll divide both sides by 5. And we got 3 equals x. So we need to determine where is that answer kind of on the number line. Is it between 0 and 15/4? So 16/4 would be 4. 12/4 would be 3. So 3 is probably somewhere around here because 15/4 is going to be 3.75. So just kind of estimating where 3 is. So 3 is within our domain. And so in this case, we do have a solution because it is inside where we expect our solution to be. And we can check our work by just double checking that it actually works. So we have the log base 5 of 15 minus 4x, but now x is 3, equals the log base 5 of 3. So log base 5 of 15 minus 12 equals log base 5 of 3. And then 15 minus 12, we have log base 5 of 3 equals the log base 5 of 3. So just like the previous example, the left side equals the right side, but we need to double check that we can actually find the log base 5 of 3. So most calculators don't have this ability. You don't have the ability to do log base 5 of 3. You can only do base 10, or you can do the natural log. So here is where we have to use the change of base formula. So the change of base formula, that was one of the properties that we learned about. Basically, log base 5 of 3 would be the same as the log of 3 divided by the log of 5. So we just need to make sure that we can actually calculate that. So on our calculator, we know we can find the log base of 3 because that's a positive number. You can take the log of a positive number. And we know we can take the log of 5. And that also works. So we don't care what the actual number is. We just want to make sure that we can actually calculate these values. Because on our previous example, if you tried to actually calculate the log of -17, you couldn't actually do it. So we just need to make sure, can we calculate this out? I don't care what the number is equal to. Can I find the log of 3? Can I find the log of 5 in my calculator? The answer is yes. So that means this answer does work. And so we do have a solution. It's 3. So I'm going to bring up Desmos again so you can visualize this. Now you may be wondering, well, how do you graph something base of 5? So I can do a subscript. So the underscore allows you to do a subscript here. So I can actually graph this, as Desmos lets me. I just have to hit the underscore to get below the log, and then I have to hit an arrow to get outside of the log. So I'm able to graph both the left side and the right side, and you can see that they intersect at x equals 3. So we don't care what the actual value is, but that is going to be the log base 5 of 3. And you can kind of verify that with your, if you do the change of base formula, if you did the log of 3 divided by the log of 5, you get 0.683. We don't care what the output is, the y value, we're just double checking our x value, and that's equal to 3. So the graph confirms that x equals 3 is a solution to this equation, and our number line basically also confirms that. Are there any questions? Okay, so I have a couple more examples like that, but I'm going to skip ahead to the other property, the other way to solve, so we can do some of those. So the inverse property. If A and Y, I think that's supposed to be X, not Y. There is no Y here. Turn that into an X. If A and X are real numbers with A greater than 0 and A not equal to 1, then A to the log base A of X equals X. Basically, if there is a log in and as an exponent and they have the same base, then they cancel out. So our textbook calls this solving by using exponential form. I call it exponentiation, and that is a term you may see other people use as well. It's just a little bit easier than saying solving by using exponential form. It's shorter. So I refer to this as exponentiation, where they kind of mean two different things. So when I say exponentiation, what I mean is that we're going to take each side of the equation and write them as exponents. They basically become exponents. So that's sort of what exponentiation is. Solving by using exponential form, what the book, when it uses that, it refers to taking your equation and rewriting the logarithm in its exponential form. You get the same result. It will look exactly the same. It's just a matter of how you're thinking about the problem. Whether you're thinking about it as terms of writing them as exponents, or whether you're thinking them as you're rewriting the logarithm. But they look exactly the same. So the steps for solving this is a little bit more complicated. So first we need to isolate the logarithm. So we want to get the log by itself. And if there's more than one logarithm, you need to use the properties of logarithms to combine them. So that's why last week were learning those properties, because sometimes you need to use those to combine them into a single logarithm. Once you've got the log equal to whatever else, then that's when you're going to do what I call exponentiation. You're going to either write both sides as exponential expressions or basically write the equation in exponential form. Then you're basically using the inverse property. So with my method, when I say I'm exponentiating, you're basically using the inverse property to cancel things out. And it just simplifies the logarithm. But if you're doing it in exponential form, you're kind of doing that at the same time. So you'll end up in the same spot. And then whatever equation you have left over, you solve. So let's see this in action. So we've got log, so this is base 10, of 2x minus 3 equals 5. So we've already got the logarithm by itself. And so this is where we're either going to exponentiate or basically rewrite in logarithmic form. So I'm going to do them both so that you can see that you're basically doing the same thing. So when I say that we're doing exponentiation, what that means is I determine the base. This is base 10 because it's a log without the number, so it's going to be base 10. And I take each side and write them as x. Whoa, my presentation just decided to close itself. Let's get back up there. Okay, so I am writing, it's doing it again. That's really weird. I'm not touching anything. Let's try this again. Okay, so I'm taking our, oh, not red. It reset my ink color. Okay, so I'm going to close my slideshow, close the PowerPoint, open the PowerPoint back up, and see if that will fix the problem. I don't know why it is doing that. Okay, let's see if I can actually write on this. Okay, so the left side says log 2x minus 3. At least it didn't actually close. Okay, 2x minus 3. And the right side is 5. So basically what I'm doing is I'm taking our original equation and making those exponents on base 10 because that's the base of our log. So I'm just basically creating those, making those exponents. And then the inverse property allows us to cancel on the left because we've got 10 and then basically log base 10. Those cancel out and you're left with 2x minus 3 equals 10 to the 5th. So that's generally how I do these types of problems. Now, if you are going to be solving using or solving by writing as an exponential expression, you are essentially taking the fact that you have some log base A or log base B of x equals y, and you're converting this to b to the y equals x. So in our case, we'd have 10, because that's the base, to the 5th power equals what's inside the log 2x minus 3. So you get the same you get the same answer. It's just written a little reversed. It's just a matter of how you want to think about the problem. Do you want to think about the problem as you're taking your base and writing them as your equation as the exponents to that base and then canceling things out? Or do you want to think about it as rewriting the equation in its exponential form? But you get the same spot. You get to the same spot. So it doesn't matter which one. So out of just curiosity, just kind of let me know. You can just type in the chat. Do you prefer the exponentiation, or do you prefer the writing as an exponential expression? Because whichever one you'll prefer, I will do that. Regardless of whether that's my natural state, that's the one that I will do. Exponential expression and exponential. Okay, so you guys are in agreement, so we will do the method that's in green. Okay. So now to actually solve, oh, gosh darn it. Okay, I am going to share a different screen. I'm not even going to try to put it in its in presentation mode. I'm going to just share in PowerPoint mode, not presentation mode, because then at least it can't kick me out. So this is what we'll do, because apparently PowerPoint doesn't like me today. Okay, so we need to solve. We've rewritten it. We have 10 to the 5th equals 2x minus 3. So we're just solving for x. So 10 to the 5th is a 1 with 5 zeros. So that comes out to $100,000, or not dollars, but 100,000. And this equals 2x minus 3. So now we're just going to solve for x. So I'm going to add 3 to both sides. We get 103. Wow, it really is doing weird. What the heck? I am not touching my keyboard. This is very strange. I'm going to move my keyboard completely away from me. Okay, so I've got 100,003 equals 2x. Make this slightly thinner. And then we're going to divide both sides by 2, and we are going to get this fraction because you can't divide 100,003 divided by 2, but you just get this. It's going to be just this kind of nasty fraction thing, but that's totally fine. So we do need to check our domain. We haven't done that yet. We need to double check that it's within our domain. So we've got inside here 2x minus 3. So 2x minus 3 needs to be greater than 0. So I can add a 3 to both sides. This gives me 2x is greater than 3. Then I divide both sides by 2. And x has to be greater than 3/2, which is 1.5. And I can guarantee that 100,003 divided by 2 is definitely larger than 3/2. And so we should be able to plug this number back in and double check that it does indeed get us 5. If we plug it in on the left, we will get 5 out on the right. So let's just pick another color. Let's check. So the log of 2 times this 100,003 divided by 2 minus 3. I just want to make sure that comes out to 5 because that's what we have in our equation, that it equals 5. So the 2 times the over 2, those cancel out. So we have log of 100,003 minus 3. It's basically the log of 100,000. And that does, you can do that in your calculator, that does come out to 5. So that confirms that our answer is 100,003 over 2. If you were to check this in Desmos, you would have the left side, which is the log of 2x minus 3, and then the right side is just 5. So you're looking for where those intersect, and 100,003 divided by 2 is going to be really big, so just kind of, I might have to actually put y equals 5 here so you can visualize. Okay, so we're looking for where these are crossing, and it's, so we've got a really big number. You can see it's getting closer. The gap between them is getting much smaller. I'm sure I might have to, okay, grab my calculator. I'm actually going to do 100,003 divided by 2, so it's going to be around 50,000. So I'm going to just cheat and move my x-axis to, let's say, 47,000 to 51,000. It should be overlapping. Oh, no, I missed the 0. Okay, trying to get it. Well, this is a situation where you may not want to try to check your answer by graphing because it is such a big number. So, but we checked it just with algebra and it works. Okay, so let's do this one. Oh, before I move on, actually, are there any questions on this one? Okay. So let's do one with the natural log because that has a special base. We just did one with log. Let's do one with the natural log, and that is base e. So we've got our natural log by itself already. We've got 2.1 equals the natural log of 6x. And so we're going to rewrite this, and I always start with whatever the base is on the natural log. So the base of a natural log is e. And then whatever this is equal to, that's the exponent on it. So that's going to be 2.1. And then that's equal to whatever is inside your log, or in this case, inside the natural log. So that's going to be 6x. So that's our first step, where we are rewriting this as an exponential expression. And now we want to solve for x. So generally what we do, especially when you have something with e, where it's, you know, a number that goes on forever, is we're going to leave it in this form and then round at the very end. So we're just going to leave it written as e to the 2.1. And we're going to divide both sides by 6. So this basically gives us e to the 2.1 over 6 equals x. And then this is where we want to round. So you're going to basically put this in your calculator in one step if possible. And most calculators can do something like this in one step. So this, when I plug it in my calculator, I get 1.3610282319, and it's basically going to go on forever, but that's how many decimal places my calculator gives me. The general rule is 4 decimal places for the most part when we do these types of problems. If you're rounding intermediately, like you might want to do 5 or 6 decimal places just to make sure that you don't have rounding errors. But I prefer to round at the end. And then we're going to round to basically 4 decimal places. So I'm just going to put a line after the 4th one. And that first number to the right of the line, if that's 5 or above, you round up. Otherwise, you don't need to round. So because it's a 2, we don't really need to round. So we're going to say that x is about 1.3610. And to check our work, because again, we do need to kind of check our work, we're going to look at what's inside our natural log, because we got to look at the domain. So 6x has to be greater than 0. And that basically, if you divide both sides by 6, x has to be greater than 0, because 0 divided by 6 is still 0. So we got a value for x that's greater than 0. And now let's just double check. If I take the natural log of 6 times 1.3610, what does that come out to? So you're going to do that on your calculator, and most calculators have a natural log button. And so that gives me 2.0999799193. Now notice that's not exactly 2.1, because we're checking. We have 2.1 equals the natural log of 6x. We're checking, does this give us 2.1? Not exactly, but it rounds to 2.1. And the whole reason you're not getting exactly 2.1 is because we rounded to get our initial answer. So when you're checking your answers for something like this, you're not going to get the exact same answer, but it's going to round to the same answer, and that's good enough. Are there any questions? Okay, so let's do this one here. This is another natural log, but we've got some things added, we've got some things like multiplied. So we need to get the natural log part by itself before we do anything else. So we are just trying to get the natural log of x by itself. So first, you're going to subtract 3 from both sides. And that gives us 8 times the natural log of x equals 4. Then we're going to divide both sides by 8 because we're trying to get that x by itself, or the natural log by itself. So we get the natural log of x is equal to 4 over 8, which is 1/2. So now that we've isolated that natural log, now we're going to rewrite it. So it's going to be e, because that's the base of the natural log, to the 1/2 power equals x. And that's the exact answer. And then if you want to round it, you're going to just have to put that in your calculator. So that gives me 1.648721271. So 4 decimal places would be after the 7. And again, because it's a 2 after the 7, we're going to just use the number 1.6487 as our approximation. So if we're going to then check our answer, we need to check it with our domain. So we just know that what's inside our natural log has to be greater than 0. So our value for x has to be greater than 0. So that's what we got. And then let's just double check that the math works out. So we have 3 plus 8 times the natural log of 1.6487. And we're basically checking, does this give us 7? So I'm going to just, on my calculator, do the natural log of 1.6487. And I'm also going to multiply that by 8 and just do that in one step. So I'm getting lots of decimal places. So at this point, if you were doing intermediate steps, I wrote down all of the decimal places. You might want to make sure you're writing down at least 5 or 6 to make sure you don't have rounding errors. But you can write them all. And then I'm going to add 3. And we got 6.999896789. And it's close enough because it does round to 7. And the whole reason why it's not exact is because we had to round for our value of x. So when you're checking your answer, especially if you're doing it in decimal form, just be aware that you're going to have to check, does it round to the same answer? It's not going to give you the exact same answer because of the rounding. Any questions? Okay, I'm going to skip ahead. Let's do this one. Okay, so this one we're going to have to use properties of logs because we have 2 logarithms. So we have to get the logarithm by itself. We can't do that if we've got 2 of them. We have to use the properties of logs to combine them first. And actually, I'm going to do the whole domain thing first while it's in separate form because it is easier to worry about the domain and think about that while it's separate. So here we know that x has to be greater than 0. And here this tells us that x minus 1 needs to be greater than 0, which when you solve says that x has to be greater than 1. So if I made a number line, I've got 0 and 1 on my number line. I know that I have to be greater than 0. I know I have to be greater than 1. And so we're looking at the overlap here. They overlap greater than 1. So whatever we solve for x, we need to make sure that it is greater than 1. So I'm going to go back to rewriting our problem. Log base 4 minus log base 4 of x minus 1 equals 1/2. So our properties of logarithms say that if you have 2 logs that are subtracted, that's equivalent to a single log with them divided. So this combines to log base 4 of x over x minus 1. So this is part of what we call condensing a logarithm. So now that I've condensed this, now I have a single log by itself. And so now I can put it in exponential form. So my base is 4. The exponent is going to be 1/2. And this is going to equal x over x minus 1. So 4 to the 1/2 power, 1/2 is the same as the square root. So this is basically giving us the square root of 4. And remember when you're solving it, you have like things with x involved. You're solving and you take a square root, you get a plus or minus answer. So we're really getting plus or minus the square root of 4, which is 2. Equals x over x minus 1. So we've kind of got two equations now that we have to solve. Because when you're solving and you take the square root, you get a positive and a negative version. So I'm going to write one of them with the positive version, and then the other one with the negative version. So we have 2 equals x over x minus 1. And then negative 2 equals x over x minus 1. To solve these equations, we're going to multiply both sides by x minus 1. We want to get rid of the denominator. And so this is going to become 2 times x minus 1 equals x. And the other equation will be negative 2 times x minus 1 equals x. So now we're going to solve for x. So I'm going to do the kind of golden yellow one first. So I distribute. 2x minus 2 equals x. I'm going to subtract 2x from both sides. This gives me negative 2 equals 1 minus 2 is negative 1x. Divide both sides by negative 1, and I get 2 equals x. So that puts us kind of right there on our number line. Now let me solve the other one. Negative 2x plus 2 equals x. So we distribute. I'm going to add 2x to both sides. And we get 2 equals 3x. Oops. Divide both sides by 3, and I get 2/3 equals x. So 2/3 would be right here. So we have two answers. One of them is within our domain. One of them is outside the domain. And so the correct answer, basically the answer is going to be the one within our domain, going to be x equals 2, because that follows that domain. It's in that area that we were looking for on our number line. 2/3 is not greater than 1, so that's going to be an extra solution that we got that doesn't actually work. And this one should be one that we can do in Desmos, not like this crazy one. Can I reset? Okay. There we go. Okay. I don't want to be where I was before. So we are going to have the left side of the equation, log base 4 of x minus log base 4 of x minus 1. Oops. There we go. And then the right side of the equation was 1/2. And so we had an answer of negative 2, and this I really should write it as like y equals 1/2. So negative 2 does not intersect. That other answer, or we had not negative 2, we had 2/3. So 2/3 is, if I zoom in, somewhere over here, it's certainly not intersecting. But the other answer that we got when we solved was 2. And you can see that, yes, at 2, the left side is equal to the right side, because when you graph them, that you do get an intersection point here. So we have just verified that the correct answer is indeed 2, and that the 2/3 was an extra solution we got that doesn't actually work because it's not going to work in the domain. Are there any questions? Okay, I'm going to do one more like this. That one also, that looks very similar. Let's do this one. Not exactly like the one that we did, but this is, you know, a good one. More complicated, more things going on. So since we've got 10 minutes, I'll do this one. So we need to get that, the log part all by itself here. So I'm trying to, this whole thing in green, we need to get by itself. So we're going to first subtract 3. So that gives us 5 times log base 6 of 7w plus 1 equals 10. Then we're going to, I don't need to show that, divide both sides by 5. Go away. I know they're hidden. And so that gives us log base 6 of 7w plus 1 equals 10 divided by 5 is 2. So we're going to rewrite this as in its exponential form. So we have 6 to the exponent of 2 equals 7w plus 1. So 6 squared is 36. So 36 equals 7w plus 1. And so now we're just going to solve for w. So we'll subtract 1 from both sides. So that gives us 35 equals 7w. And when you divide both sides by 7, 35 divided by 7 is 5. So we get 5 equals w. But we need to check our domain. So our domain is the inside of that log, which is 7w plus 1. That needs to be greater than 0. So when I subtract 1 from both sides, 7w needs to be greater than negative 1. And when I divide both sides by 7, w needs to be greater than negative 1/7. So 5 is definitely larger than negative 1/7. So it is within our domain and it will work in the equation. Are there any questions? I have no idea what all my notifications are, but it's certainly not really hidden while I share my screen because the notification bar keeps coming up. All right. Well, I think you guys seem to have a good handle. You haven't had any questions. I do have like, you know, extra. I always over plan, but I think that it's pretty clear. You've got some good examples here. So if you do run into issues, feel free to reach out to me. You know, I'm happy to help. But that's pretty much all I've got for you guys. So hopefully, you know, this is the last week of class. You guys feel pretty confident about week 8 stuff. It's not so bad. The final does cover weeks 5 through 8, so you're going to want to review previous week's work, like the quizzes and stuff like that, since there will be some reusing of problems. But you guys are all set. So thank you guys. Thank you so much for attending, and it's been wonderful having you guys come to the lives. I can't say I'll see you at the next one because I won't, but I did just find out today that I'm going to be teaching pre-calc next term. So if you do have to take pre-calc, you'll have me because I just got that notification. So maybe good news, maybe bad news, you know, depending on how you feel, but you might see me again. So, all right. Steven says no more math. That's totally fine. Erica, I'm glad that I have not let you down, having you for multiple classes. So, all right. Well, I'll let you guys go, and I will, you know, probably see you sometime, maybe at graduation, who knows. So take care.